Hey everyone, and welcome back to my channel. In this video, we are going to discuss the second example of Newton-Raphson method, which we are going to solve it using by hand calculations. So in the previous video, we have some different question, but in this video, we are going to discuss about a different question in which firstly, we are going to develop an equation. Secondly, we check the interval that either our root lies in that interval or not. And if our root lies in that interval, then we will choose one initial guess according to our choice. And then we are going to apply the Newton-Raphson method. So let's get started. We have a question that find the cube root of 48 on interval 3, 4 by Newton-Raphson method correct up to 4 decimal places. So we need to check the accuracy till 4 decimal places. Secondly, we need to find out the equation that is extracted from the statement of cube root of 48. So initially, we are going to let any variable to cube root of 48. So we just write it like this, that this is a cube root and this is a 48. So we need to solve it first by taking a cube on both sides of the equation like this, and this will cancel out with this, and we will get that p cube is equals to 48. So after that, p cube minus 48 is equals to 0. So this is basically our function that we are going to use it for Newton-Raphson method. So after finding out the function, we need to find the derivative too. So f prime of p is equals to 3p square. So that is not equals to 0. So we can easily proceed. After this, we are given with an interval that is 3, 4. So first of all, we are going to check that either our root lies in that interval or not. So in order to check the availability of root in this interval, I am going to substitute 3 into the function and then 4 into the function. If they gives us an opposite signs, it means that the root lies in that interval. So for that, I am choosing my first point, that is 3, and I am putting into my function. So it's 3 raised to cube minus 48, that is equals to 27 minus 48. So the answer should be negative of 21. Now I'm going to substitute my next point, that is 4 into the function. So that should be 4 raised to cube minus 48, that is equals to 64 minus 48, and the answer would be 16. So by putting 3, we will get a negative value, and by putting 4, we will get a positive value, that is 16. So it means that our root lies in that interval. Now it's our choice that which point we are going to choose as a first approximation. So we can easily choose 3, we can easily choose 4, or in between we can choose 3.1, 3.2, 3.9. So it's according to our own choice. So I am choosing P naught, that is equals to 3.6, and this is my first approximate root that I am using to perform my iteration further. So let's begin with the first iteration. Okay, the customized formula for the first iteration for this question is P1 is equals to P naught minus f of P naught divided by f prime of P naught. So I am going to evaluate the few points by putting the P naught into the function and its derivative. So f of P naught is equals to P naught cube minus 48. So value of P naught is 3.6. So I am going to substitute at the place of P naught minus 48, and we will get the answer negative of 1.344. That is our f of P naught. Secondly, we need to substitute in its derivative. F prime of P naught, that is equals to 3 P naught square. So it should be f of f prime of 3.6, that is equals to 3.6 raised to square, and from here we can easily get 38.88. Now we are going to substitute the function and its derivative value back into this formula at the respective places. So P1 is equals to 3.6 minus, and we have negative 1.344 divided by 38.88. So after solving it, we will get the value of P1 3.634567. That is our P1. Now we will move toward the second iteration. For second iteration, our customized formula is P2 is equals to P1 minus f of P1 divided by f prime of P1. Now we are going to find out the f of P1. So for that, I am choosing my function and I am going to substitute it. So it is P1 cube minus 48. So that should be equals to 3.634567. That is equals to 3.634567 raised to cube minus 48. So after solving, we will get the answer 0.012910. So that is the answer of f of P1. Secondly, we need to put in its derivative. So that is 3P1 square. So after substituting it, we have 3.634567. That is equals to 3.634567 whole square. So after solving, we will get 39.630231. Now we need to substitute f of P1 and f prime of P1 back into the formula at their respective places in order to find out the value of P2. So we have P2, that is equals to 3.634567, that is the value of P1, minus 0.012910 divided by 39.630231. After solving, we will get P2 is equals to 3.634241. Now we need to compare our values in order to check the accuracy that either we achieved our required accuracy or not. So the value of P1 is 3.634 and the value of P2 is 3.6342. So till 3 decimal places, our answer is almost similar, that 3.64, and here we have 3.634. But it is mentioned in the question that we need the accuracy till 4 decimal places. So for that, we need to go for third iteration. So the customized formula for the third iteration is P3, that is equals to P2 minus f of P2 over f prime of P2. Now we need to find the value of f of P2 and f prime of P2. So f of P2 is equals to P2 cube minus 48. So that is equals to f of 3.634241. That is equals to 3.634241 cube minus 48. So we will get 0.5 times 0 and 7, or we just write it like this, that 7.0 into 10 raised to the power minus 6. Now we need to find f prime of P2. So that is 3P2 square. So we have 3.634241. That is equals to 3.634241 whole square. So after solving, we will get 39.623122. Now we need to substitute the value of f of P2 and f prime of P2 back into their Newton-Raphson formula at their respective places in order to find out the value of P3. So P3 is equals to 3.634241 minus 0.12345 times 0 over 7 divided by 39.623122. So after solving, we will get the results 3.634240A. So we need to compare our P2 and P3 values in order to check the accuracy that either we achieved or not. So the value of P2 is 3.634241 and the value of P3 is 3.634240. So if we check the accuracy, so we have till 4 decimal places we have 3.6342, and for P3 we have 3.634. So after 3 iterations we achieved the accuracy till 4 decimal places. So we can simply say that hence the approximate root correct up to 4 decimal places is P is equals to 3.6342. And that's it. We just found the root of the equation step by step using the Newton-Raphson method, and our answer correct up to 4 decimal places is 3.6342. If this helped you out, don't forget to like the video, subscribe to my channel, and drop a comment if you want to see more step by step numerical methods solved by hand. So thank you so much for tuning in. Take care.